Okay, what we're doing in this example is we're allocating a task to one of four operators, and there's four tasks basically that each of the operators are going to do. Now what they've done through whatever trial and error or research has found out that the operator A takes 4 to do task 1, 9 to do task 2, 8 to do task 3, and 13 to do task 4. And what we're looking for is a way to allocate these tasks to these operators here to minimize the time. Alright, so to do this, you could brute force it, trial and error, and see if you can get it out, but the best way to do it is to use the Hungarian algorithm. Alright, so the first thing we're going to do in the Hungarian algorithm is you need a couple of grids, or as you do a second phase of the Hungarian algorithm, just draw up another grid. Okay, but I've pre-drawn 6 here just in case I need that many. Alright, so the first thing we're going to do is what we call row reduction. Alright, what we do is we look through a row and we find the lowest time or lowest cost in that row. In this case, the lowest number is 4, and we subtract 4 from each of the elements in the row. So we've got 0, 5, 4, and 9. We do the same thing for each row. It's 5 in this case. So 0, 6, 5, and 11. In this case, it's 3, 0, 9, 4, and 9. Last row, 6, so 0, 2, 0, and 9. Okay, now comes the bit, it's a bit strange, but what we're going to do is we're going to try for an allocation now to see, after we do a row reduction, whether there's an allocation we can do straight away. Now what I do is I try to put the smallest possible line, smallest possible number of lines through the zeros in either the rows or the columns to see whether there's a potential allocation. So I'm just going to do it first. So one line going through there and one line going through there. So each column or row with a 0 in it must have a line going through it. Now what you'll notice that I can do this with 2 lines in this case. Now what we note is that there's 4 operators here, or 4 rows. That means we need 4 lines, and once we get 4 lines crossing out the zeros, it'll mean that we have got an allocation. So what this is basically saying is that there's no allocation just at the moment. So the next thing we do is what we call column reduction. That is, we look through each of the columns now and we see if we can actually reduce them using the same method as the row reduction. Right, now whenever there's a 0 in any of the columns, it means that's exactly the way it's going to be because the smallest number is 0. But this column here we can reduce by converting that or removing 2 from each of the elements, 4 and 3. This one needs to stay as is because there's already a 0 in it. And this one we can certainly remove 9, which that becomes 0, 2, 0, and 0. Alright, so let's see what we've got here. Now, I'm going to put a line through there, a line through there, and a line through there. Now, the minimum number of lines needed to cross out all of the zeros was 3. We need 4, so there's no allocation just yet. Alright, so this is the really strange part. Okay, and again, I can't go into how it works here, so just check out another video or heaps of videos on YouTube about how this part of the algorithm works, because this is the least understood part. But what we're going to do is look at the uncrossed out numbers here. They're in the middle there. What we're going to do is choose the smallest number of those 6 numbers, and that's 3. And we're going to remove 3 from all of those numbers. So we're going to get 0, 1, 1, 2, 3, and 0. Nope, my bad. 1. Okay, I'm getting myself confused. Alright, I'm removing 3, so let's just confirm 4 take away 3 is 1. Alright, back in business. Alright, now this is strange. Okay, now what you'll note here is this 0 here has been crossed out twice. Line, line. And so has this one. So what we're going to do is, instead of adding it, subtracting 3 from it, we're going to add 3 to it. Again, this is weird, so I can't really explain why in this video. This is the algorithm. Let's do it. Alright, any number that's been crossed out once only just goes back in, or gets written back in. 0, 0, 0, 0, 0, 2, and 0. Alright, let's see if we can get an allocation now. Line, 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 and we're in business. Alright, now because we've got 4 lines here, that means we've got a potential allocation. Alright, so let's see what it is. So A, B, C, and D are my operators. Now, I know that A can do either task 1, task 2, or task 3, because they're all zeros. So which one do I give them? Don't know. But let's have a look and work out, well, what's going to happen with B? B can only do task 1, because that's the only task that has come up with a 0 in B's row. So that means B must do task 1. Alright, let's have a look at C now. C can do task 1 or task 4. I just allocated task 1, so C must do task 4. Let's have a look at D. D can do task 2 or task 3. Now what can A do? Because they're the only remaining tasks as well. A can only do task 2, so we've got to allocate task 2 to A. Thus, task 3 is allocated to D. Alright, so that is how the tasks should be assigned. Often questions will talk about what is the total time. So let's find out. A gets task 2, so that takes 9. B gets task 1, that's 5. C gets task 4, 12. And D gets task 3, which is 6. 18, 23, 32 is the time it will take. So there's the Hungarian algorithm for you. The only thing that will change is that you may, on this step here, not be able to do 4 lines. You might only get to 3. In that case, just keep going. Do the same process that we did over here again until you get the 4 lines going through and you can get an allocation.